Hi, everyone. As Kate mentioned, my name is Molly Welch, and I'm a partner here at Radical Ventures. We're an AI-focused venture fund, and we're thrilled to have you all here for our annual Masterclass. We have a special session today. We have the privilege of speaking with Jim Fan, a leading voice in AI agents and robotics research. Jim is fresh off of NVIDIA GTC. I think he's still in DC, so we're going to have a lot of fun things to speak about today. Jim is a director and a distinguished research scientist at NVIDIA, where he co-leads development of the Isaac GR00T platform for humanoid robotics and heads the GEAR, or Generalist Embodied Agent Research Team. Jim earned his PhD from the Stanford Vision Lab, where he was advised by Fei-Fei Li. His groundbreaking work includes Voyager, the first AI agent to master Minecraft through lifelong learning, MindDojo, which won the NeurIPS 2022 Outstanding Paper Award, and Eureka, a project teaching robot hands complex dexterous tasks like pen spinning. Jim has also the unique distinction of being OpenAI's very first intern back in 2016, where he co-developed World of Bits. And we're going to hear a little bit more about that later. Jim, we're thrilled to have you. Welcome to the Radical AI Founders Masterclass.
Thank you so much for having me, and thanks for the very kind intro, Molly.
We're really pleased to have you. Jim, I want to start with this incredible journey that you've been on from OpenAI, Stanford's Vision Lab, now leading embodied agents at NVIDIA. Walk us through your journey, your decision-making processes at each transition. And in particular, we want to hear about what drew you from academia to some of these roles in industry.
Wow, that's a huge question. So let me break this out. I think, in retrospect, it's really serendipity and then following some good vibes. So I'm calling it vibe research that I did over the last like 10 years. So I would say the vibe I was following is basically two things. One is picking hard problems, and the second is to seek simple solutions. And I feel like a lot of the opportunities that I hopped on, a lot of the projects are all following these two principles. I got interested in deep learning first in 2012, and that's when AlexNet first came out. And I was really attracted by its elegance, right? Like, before 2012, computer vision is a very complex pipeline. You have hand engineered features, right? All the geometric analysis on pixels, and then SVM and a bunch of statistical methods to reach a classification of the image. And all AlexNet did was mapping pixels directly to a category, right? So like 1,000 different objects, and then you pick one out of 1,000. That's it. Very simple, very elegant. So my first deep learning research project was actually an astrophysics project at a Columbia Computer Vision Lab. So the goal is to estimate gravitational lens parameters from astrophysics images. And that was around 2013, summer of 2013 to 2014. And at that time, it was still very kind of traditional pipelines, right? Like you have SIF features and SVM to do classification. I decided to implement something like a convolutional neural net, but at that time in MATLAB. And then I found that it actually blew everything out of the waters. It's a very simple method. If you have a small training set, you do gradient descent, and the system programs itself. So that was kind of my first contact with deep learning. And then in 2015, I joined Engineering's lab to work on a project called Deep Speech. And as the name suggests, it's for speech recognition. And again, at that time, there are a lot of traditional systems that first do audio segmentation and then phoneme classification, wave feature extraction, and finally a ton of probabilistic scoring models. But at that time for deep speech, we believed in end-to-end. Basically, you take a raw audio wave in and then output text, a sequence of text. And that's it. At that time, we didn't even have transformers. So it was like very old sequence models called LSTM. And we talked about having a data pipeline. We talked about scaling up data and the model back in 2015. So it was a very simple, elegant approach. And it turns out that it solves speech recognition really, really well, much better than traditional systems. And then 2016, that's when that was the last summer internship before I started my PhD. And I heard about a new company, a new startup with a bunch of brilliant people. And that startup turns out to be OpenAI. And I reached out, and then they said they don't have an intern program, but maybe it's time to create one. So I had the great honor to join OpenAI in that summer. And the project I worked on was called World of Bits. I was mentored by none other than the great Andre Kaparsi. So it was his idea, his vision, and I was very gladly part of that vision. So the idea of World of Bits was that we wanted to teach an AI agent to learn to use the web browser by observing the pixels rendered from the browser and then outputting keyboard and mouse controls directly. It's actually part of a much larger initiative at OpenAI at that time called Universe, and it's more general. Basically, anything that you do on a computer can, in principle, be this interface of mapping pixels from the screen to keyboard and mouse actions. So you can play games, you can use software like Photoshop, Microsoft Word in exactly the same way. So that project is really about building a general purpose interface for the agents. And once you have that general purpose interface, then you can enable end-to-end agents that maps from pixels all the way to actions. I think at that time, it was revolutionary. Like I have never seen anything like that before, right? Like we were, the AIs at that time were struggling to play very simple games, let alone solving general purpose computer use. And we were using reinforcement learning. There was no foundation models, right? Everything was kind of trained from scratch. So in 2016, that was way, way ahead of its time. But this year, 2025, right? 9 years later, we kind of, history repeats itself, or really it doesn't repeat exactly, but it rhymes, right? We are starting to solve the world of bits using modern LLMs and also reinforcement learning. But this time it's not from scratch, right? It's RL reasoning on top of LLM. And then we have things like computer using agents, MCPs that can use tools. We're finally starting to solve that. So even though we were not able to completely solve in 2016, but I think that summer's internship really shaped my research taste, which is that the data pipeline can be very complex, but the model interface needs to be very simple because only simple and elegant methods can leverage all kinds of the data sources. Only the simple methods can scale the best with compute, right? It's really a perspective on how to approach these hard problems. So that was the summer. And then I started my PhD with Professor Feifei Li at Stanford. And as everyone knows, Feifei doesn't need an intro. She's the world-renowned scientist on computer vision. She was known for ImageNet. And at that time, computer vision was about like image segmentation, benchmarks, right, classification, video, like video segmentation, video annotation, and so on. And we call those static computer vision, right? You have a data set, you have static images and videos, and you map that to some sort of labels. Now, Feifei's vision was that static computer vision is hitting a wall. And the next big revolution would be embodied vision, meaning that computer vision should be solved with agency. So you can have visual agents in simulation and in the real world. And the visual agents in the real world is basically robotics. So from 2016 to 2021, over the 5 years I was at the lab, I basically witnessed Feifei's lab's transition from static to embodied vision, and then to have a new North Star of solving these kind of robotics and then visual understanding, but in an active perceptive loop. So that was very inspiring. And again, that's a kind of a second major reshaping of my research taste. And then graduated, went to NVIDIA. NVIDIA is still my first and only full-time job, and I've been carrying on a lot of ideas from my PhD work into building general purpose robotics and robot foundation models. And sorry, that's a very, very long intro, but I do hope to look back and see kind of all like how all these threads tie together. It's vibe research.
What a wonderful framing, vibes-based research, and so many great threads that I'm excited to pull on in our conversation today over the several exciting acts of your career so far. And maybe to touch on this first act, your internship at OpenAI, which feels, it kind of insane to conceptualize OpenAI in the earliest days. Also, this type of research, which, as you said, is so relevant today and so much in the zeitgeist. These same ambitions are now possible, uniquely possible with frontier models and high compute RL, as you described. So take us back to this first internship at OpenAI 2016. This is World of Bits before LLMs become really central to the work at OpenAI. What was that experience like? And how did it shape your perspective on AI research and the broader industry?
Absolutely. At that time in OpenAI, there was the OpenAI Universe that I work on, and there was also a few other exciting projects. One is the Dota project, so that was called like OpenAI 5, basically to train RL agents to solve games like Dota. And there was also actually a robotics project at that time to use high degree of freedom. Shadow hands to solve Rubik's cube. So later we're going to talk about some research like Eureka that actually reinstantiate some of these ideas and then train the dexterous hands to do a lot more. So I think at that time there are a lot of building blocks, even as early as 2016, and the most significant one being reinforcement learning and sequence models. But it wasn't until 2017 and 2018 where kind of the transformer architecture comes and it becomes this data sponge where you can really scale on the data and compute, and you will see magic happening from pre-training. So after that moment, we're starting to get into the pre-training age of foundation models, and then RO comes back. And as I mentioned, right, history doesn't repeat, it rhymes. RO comes back and then really takes off from this strong foundation, right? Like the foundation needs to be able to do reasoning and needs to be able to kind of do in-context learning, all of those capabilities, and then RO can push it right to the next frontier. So that experience at OpenAI also inspired one of my first projects at NVIDIA. So that was a pair of projects you mentioned at the beginning, MindDojo and Voyager, where we wanted to have these embodied agents to solve Minecraft. And I think, for that project was also one of my excuses to play games at work. It's all for science, right? I'm collecting data, right? I'm not slacking off. I'm collecting data for
All in the
science.
spirit of data collection.
It's all for AI. It's all for pushing the frontier of AI. So I think what was fun about that project was Minecraft is this open-ended environment. It's also a simulation, meaning that you can basically generate infinite data of almost infinite diversity in Minecraft. I've seen people doing crazy things inside this sandbox game, right? Like building the Hogwarts castle brick by brick, or even building a functioning CPU circuit using those like fundamental building blocks in Minecraft that actually makes the game Turing complete, right? So this game has infinite diversity, yet humans play it very well, but for AI, it was lagging way behind, right? It couldn't even do some basic things. So at the time when we started the Voyager project, that coincides with the introduction of GPT-4. That was the first foundation model that can do coding extremely well. So how we apply GPT-4 to Minecraft is that we give it an API so that GPT-4 can read the instructions of the Minecraft API and then write code. And then we execute that code in the Minecraft simulator to drive the agent to mine blocks, right, to explore, to travel, right, to dig, to craft new items. So basically, we turn the game into a text environment, and it communicates by code. And then we found that GPT-4 is not only good at in-context learning, it's also very good at a capability called self-reflection. So it can run into bugs, right? Like no one can write perfect program at the beginning, like in one shot, not even experienced programmers. You got to iterate. And that's what we observed with GPT-4. It writes code, tests it, and the code breaks, it sees bug, it debugs, it tries again. And once it writes a good code, a good piece of code, it would commit. to a memory. So we call this kind of an on-the-fly code repo. So GPT-4 will save some of the code it wrote to this repo, so later it can retrieve it if it sees a similar situation. And in this way, we couldn't actually fine-tune the parameters for GPT-4, but it still learns over time because it's committing code, retrieving code, and doing trial and error, and it accumulates the context as it goes. So it's a kind of in-context lifelong learning. And I find that idea really fascinating because at that time, right, like people were really trying to experiment and see, right, what are the capabilities of these coding frontier models? And Voyager provided one way to build a very complex agentic system on top. And then 2 years later, these days, the agents are a lot more powerful. Like self-reflection, people don't even talk about it. It's kind of a given, right? Like all the Claude and Cursor of the world, they can do debugging super well. They can go on like a 30-minute session to implement a pull request, and then it goes on autopilot, and it typically does the job pretty well. And it's also able to call all kinds of tools, like web browsing, connecting to MCP. So I think the field has gone way beyond Voyager, way beyond Minecraft. So that was really exciting to see. Now, what was lacking a bit from Voyager was actually that we didn't solve the motor control problem and we didn't solve the perception problem. We essentially simplified the problem by turning Minecraft into a set of code API and code execution environment. But later, I have come to understand that really the most difficult part may not necessarily be the reasoning side. I think the field is already solving reasoning quite well. The most difficult part of embodied agent is actually the low-level control, the part where you interact, right, with the low-level physics. In Minecraft, it's the game physics, but in the real world, it's the actual physical reality that we're touching. And that makes the robotics problem a lot harder.
Very cool and incredibly clever. The approach remains incredibly clever even as the technology has progressed. So thank you for talking us through it. I, I'm curious, MindDojo and Voyager represent this progression towards agents that learn autonomously or more autonomously through exploration. What do you think are the key remaining bottlenecks for creating truly self-improving agents?
I think two things. So there's a popular work called Thinking Fast and Slow from psychology. Basically, it says that all the intelligent beings, like humans, have two systems. So system two is like slow and deliberate and does reasoning, and system one is fast, reactive, and intuitive, right? So the two system approach to agentic AI. I think right now the system two is progressing quite well. It's not perfect, but I think there are like many ways to improve system two, right? Like more data, more environment that we can plug into the frontier LLMs so they can do reinforcement learning. These days, the frontier LLMs are really bottlenecked by the diversity of the environment, not just the pre-training data, right? We are kind of in this new era of RL post-training. So that's on system two. And system one is still remains challenging because computer vision is not solved. It's also much harder to collect data for system one. And I think that's also a good segue to maybe talk about Project Good and robotics.
It's a perfect segue, which is what I want to talk about next. So, you're leading physical AI research through the Gear team, Project Groot for general purpose robotics, as you described. What do you think is the grand challenge for robotics? Why is it so hard? Why is system one, which is so easy for us, system two is the hard piece? Why is system one so hard in robotics?
That's a great question, Molly. Um, well, first, for the audience who's not familiar, Project Good is NVIDIA's moonshot initiative to solve general purpose robot AI. And I think to solve this, first we need to define a milestone, right? Like, what is this grand challenge? So here's my proposal. Suppose on Sunday night, you hosted a big hackathon party, and you wrecked the house, right? Like pizza everywhere. It's a complete mess. Now you go to work on Monday, and you come back home to a clean house and a candlelit dinner, and you couldn't tell if a human or robot had been there. And I'm calling this the physical Turing test. And it's a really a shout out to the actual Turing test, right? Like that Turing proposed. And we as a community more or less solved the Turing test. When you're chatting to a chatbot, you can tell it's very easy to fool a human now. But what about the physical Turing test? I think it's deceptively simple, right? It sounds so simple, so intuitive, but it's perhaps the next or the last grand challenge in AI. And Molly, as you hinted, right, like it's so easy for humans, but really we're at the thick of the Moravec's paradox, where things that are easy for humans are actually incredibly hard for the machine. And why is that? I think the main problem is the data problem. I listened to Ilias talk, and he famously said that LLMs pre-training is hitting a wall because we're running out of data, right? Like the internet, we only have one internet, and the internet is the fossil fuel of AI. But I would say that you guys, LLM researchers, are so spoiled because you at least you have the internet to train on. And we roboticists, unfortunately, we don't even have that. So let me share a screen. I would love to show the audience. Robotics is a very visual thing. I think one video is worth 10,000 words. So let me share. And Molly, tell me if you can see it.
We can see it. We see the grocery in
Amazing.
NVIDIA HQ.
Grocery in NVIDIA HQ. So this is like a typical data episode that we collect for robotics. And this is the input to the robot. And actually, this is the output. That's what the robot joint control or the motor control looks like. It's a high degree of freedom, high dimensional continuous signal. And unfortunately, you cannot scrape this signal from Wikipedia. So we have to collect the data in some ways. So what we do is through a process that we call teleoperation. So here, this researcher is wearing a VR device where it's streaming her hand pose in real time to the actual robot. So the robot is physically mirroring her movements. And then in this way, we can control the robot to do a lot of tasks, like here to pour honey over a toast. And the researcher basically sees the robot actions right through this egocentric camera. So unfortunately, this process is very manual, right? You can see it's very tedious, and it hits the physical limit of 24 hours per robot per day, right? But actually, that's the upper bound. The robots are fragile. We babysit them all the time. They throw a tantrum, and if the robot god is merciful on that day, we may collect up to like 4 hours of high quality data, right? So it never hits 24 hours. So really, it's a kind of human fuel that we are collecting for the robot. And then that's compared to the fossil fuel, right? That Ilya said, all the LLMs are pre-training on. So the question is, how can we get the nuclear fuel for robotics, right? What is the clean energy? What's a way to generate almost infinite amount of data, right, to feed our pipelines? So here is a quick pyramid, right? The real data is on top, is the smallest amount. The web data is huge, and then synthetic data, right, will be the future. So it's infinite in principle, but it's limited by PhD brain cycles because we need to come up with novel methods to actually generate the data, and also by the compute. Right. So the more you buy, the more you save. This message has been approved by my boss. And I want to show some new research that we're doing on synthetic data. So Molly, at the beginning, you mentioned Eureka. Yeah, I want to show this. So it's a technique that allows us to train a high degree of freedom robot hands to do pen spinning at human level. And I want to admit that I am a subpar human. I can never really do pen spinning, and I gave up a long time ago in my childhood. So it's really glad to see my AI avenging my poor skills, right? How do we get the data to train this? The answer is there is actually no supervised data set. It's all done by reinforcement learning in massively parallel simulations on the GPU, because luckily, all the physical equations are mostly just matrix multiplications. So you can run this on CUDA, simulate reality, at 10,000 times faster than real time. And then you can transfer this to the real world. And how do we do that? Through a process called domain randomization, where for the 10,000 different environments, you can vary their gravity, friction, and weights, and then you follow the simulation principle. So suppose an AI model is able to master 1 million realities with different physical parameters, then it's highly likely that it's going to zero shot the 1 millionth reality, which happens to our own physical world. And just to kind of show some quick videos, we can run like a robot dogging simulation and then transfers to real world. We can control four-finger hand to manipulate a cube. And this one is most interesting. We have a robot dog walking on a yoga ball and try to stay balanced. And actually, the yoga ball is very hard to simulate. It's bouncy, right? It's soft, but actually, we don't even simulate that. It's just a hard sphere that we do, but we do a lot of domain randomization. And then, you know, we're roboticists, we're weird, so we just transfer and run it in the streets. Yeah, it's an actual robot dog running on a yoga ball in the streets. Sometimes I feel like I'm the director of a Black Mirror episode. Yeah, it's just so weird. Actually, my friend, after seeing this video, he told me that he tried a yoga ball on his own dog, and it couldn't do it. So in a sense, we have achieved super dog performance. And of course, we can scale this to a lot more complex embodiment, like an army of humanoid in sim. And these humanoids are going through 10 years worth of intense training in only 2 hours of simulation time. And then with that much data, we can train a 3 million parameter neural network. Note that it's not billion, only 3 million parameter to control the robot body to stay balanced, walk, run, jump, and dance. So basically, this small neural net that we train in simulation, it can capture this kind of subconscious motor coordination that we as humans do all the time. And it runs at millisecond scale on a GPU on board. So this is actually shot in the NVIDIA headquarters, the Voyager building. So if you visit Voyager, you might run into these little guys and don't be a stranger, wave, say hi to the robots running around. And also don't forget to visit our robot hospital. These little guys work as hard as our researchers and no robot harmed during filming.
Too good. Another day in Silicon Valley where you see a robot dog on a yoga ball. You see a robot getting CPR at NVIDIA HQ. We
Yes,
live in an amazing world.
it only happens in Silicon Valley. We are the weirdest people.
Exactly. We're very weird. We're very weird. Taking us in another but related direction, we talked about synthetic data, we talked about teleop. I want to hear your view on world models, which is this newer paradigm pioneered by some of the folks, a few of the folks that we've talked about today, and may have a role in the data in helping solve the data problem for robotics. I'd love to maybe hear you talk a little bit about world models, where you think world models fit into this overall picture, whether they can help on the data side. Would love to hear your views there.
Absolutely. So first, let me kind of define world models. I think the term means different things to different researchers. And to us, world model means this kind of um, pre-trained video foundation model that can take as input actions and then predict the future in pixels. That's an operational definition of world model that I work with on a daily basis. Now, why are these models so powerful and so useful? I really like to think of, just to make an analogy, I really like to think of video world models as kind of like Doctor Strange, right? They have seen almost every possible physical phenomenon from billions of internet videos. And the model basically learns a superposition of visual realities. It's just like LLMs learns a superposition of all kinds of different personalities from all the novels and articles it read on the internet, right? So the video models is a superposition of visual realities. And when you prompt these models, you basically collapses, you basically collapse the infinite possibilities into one chosen future. So in this world, in this way, these video generation models are actually counterfactual simulation engines, right? Like they have seen all the physics and they know how things should act given certain actions. So let's say you drop a bottle of water, you drop a cup of water, it will know that the water will spill. It has this predictive ability. And for robotics, this ability is super important because actually for humans, when you do certain actions, right, you have this mental model of how the actions, like what kind of results will the action yield. And then you plan implicitly to optimize for actions. So we see this world model as kind of an alternative and a very powerful new way to either generate data or even become the backbone for a robot brain. And I would like to actually share screen again. I want to show very recent work from our lab. So yeah, let me share screen. Um, we actually just showed this video like a few minutes ago, and actually I tricked all of you. There is not a real pixel in this. It's actually generated entirely by a video world model. So we call this idea and the algorithm Groot dreams, right? Like does humanoid robot dream of pixelated sheep? That's where this name is inspired by. So how it works is you take a pre-trained video generation model, and then you can fine-tune it on the robot data that you collected. And we found that because of all the pre-training on billions of internet videos, this world model is actually able to learn the constraints, the physical constraints of the robot, right? All the mechanical kind of parameters of the robot. And then it's able to simulate how the robot will behave given a small amount of post-training data. So here on left and right, it's actually the exact same initial frame. And the only difference is you give it different prompts, and then it will simulate different futures. So on the left is pick up the apple and place on the pen. And on the right, pick up the can and place on the pen. And the model knows how to follow these languages. And all these pixels are generated. And also the other good thing is because it's an end-to-end learned model, it doesn't care how complex the scene is. And I think that's its strongest advantage over traditional graphics pipelines, where the more complex the scene is, the more effort artists need to put, and also the more compute you need to do ray tracing and so on. So here is a much more complex scene. The video world model doesn't care. It's going to simulate just as well. And then we're able to run this on a lot more diverse scenes. And you can see like all the reflection, right? All the complex reflection on the silverware is able to do that without implementing a ray tracing algorithm explicitly. And then using this pipeline, we can generate lots and lots of synthetic data that we call neural trajectories. And we can add this as if they're real robot data, and then train on those data together, and we'll be able to perform a lot better on the robot task. So I would say that world model is still at its early stage. We have some initial ideas, early ideas to make it work, but a lot more research needs to be done.
Very cool. Thank you for sharing that. And again, amazing to see the demos. You mentioned robotic brains. I want to zoom out and talk a little more broadly about robotic foundation models. What are the principles to build robotic foundation models, and where are we in the development of robotic foundation models today?
Absolutely. And I think I'm very much following the vibe that brought me, here at this moment in the first place. So I mentioned that I was basically choosing hard problems and then selecting for simple and elegant methods because they scale the best with compute and data. And it's the same principle that I'm applying to robotics. And we can summarize that in four words: data maximalist and model minimalist. I mentioned there are many different ways to collect the data. right? We can collect through teleoperation. We can generate data using simulators like Isaac Lab. And then we can also generate data using world models. So the data pipeline can be very complex, but the model should be as clean as possible, as end-to-end as possible. Because in this way, you can leverage all the different data sources without building separate training recipes and loss functions for the models. So it takes as input pixels and then directly output the motor control signals that you saw, like the high dimensional continuous signals. And earlier this year, we open source a model called GR00T N1 that operationalizes this approach. So the GR00T N1 model, it's got System 1 and System 2. Right, System 2 is a VOM that does reasoning. System 1 is actually a diffusion model that renders the actions at more than 100 hertz. And despite it's got this kind of modular approach, it's actually an end-to-end, fully trained model through backpropagation. So that's how we approach it. And we're building an ecosystem. So we open source everything. We open source the training recipe, the model parameters. And if you search for Isaac GR00T online, you can download the model and try it out today.
It's a hugely valuable contribution to the ecosystem. So thank you for sharing and encourage others to check it out as well. We talked a little bit before, Jim, about the GPT-4 moment in robotics.
Yes.
What's your prediction? When will we get the GPT-4 moment in robotics? And what are the research and commercial problems that need to be solved before that happens?
I did ask this question a lot, and thank you so much, Molly, for bringing this up. So I think the community tends to, in general, overestimate the short term and underestimate the long term. I would say I don't know for sure exactly when the GPT-3 moment for robotics will happen, but I know for sure when it will certainly happen. So here's kind of my reasoning, right? So this year is 2025, and AlexNet was introduced in 2012. Actually, AlexNet was, held as this milestone, right? Huge revolutionary moment. But does the audience know how crappy AlexNet was? It's a horrible model. What AlexNet did is classifying objects, right? Like 1 out of 1,000 categories, like cats versus dogs versus airplanes. And its accuracy was only 62.5%, meaning that it confuses cats and dogs and airplanes more than a third of the time. It's completely unusable, right? Even though it was a revolution from a methodology point of view, performance was super bad. And then fast forward to 2025, what do we have today? We have LLMs that pass the Turing test. We got the latest coding models and the reasoning models winning gold medals at IMO. And then AlphaFold just won a Nobel Prize. And that's what's happening in 2025. It's crazy what happened in the last 12 years. And then it so happens that technology doesn't progress linearly. It's exponential. So if we take 2025 as a middle point and we add 13 years from now, that would be 2038, right? Where we're in the middle between AlexNet and 2038. And then PhDs procrastinate. So let's round up, give them 2 more years. By 2040, I believe the number of robots, intelligent robots in the world will be more than the number of iPhones. And I say that with more than 95% certainty that it's going to happen.
It's a provocative framing, and I want to think shorter term for a moment. When you think about models today and the next 2 to 3 years, many folks are thinking about what the next chapter of their journey looks like, whether that's starting a company or joining. Given models'
Absolutely.
capabilities today, which application areas do you think have the right combination of market readiness and technical feasibility to be really tractable in the next 2 to 3 years?
That is a great question, and let me also zoom in a little bit on the shorter time horizon. And again, this year is 2025, and if we look back to May 2020, that was when GPT-3 was first introduced. And from GPT-3 to winning a gold medal at IMO, I think that roughly takes roughly three iterations, right? So there is SFT, and then there's ROHF, right? Reinforcement learning from human preference as kind of two big breakthroughs, and then reinforcement learning uh, like the O3, the OpenAI O1 and O3 style, like RL for reasoning. So roughly three major model capability breakthroughs carried us from 2020 to 2025. So if we add 5 more years, that will be 2030. So I think in terms of methodology, right, like the breakthrough in robot foundation model, probably 3 takes 5 years will get us there. So now, what do we do in the next, right, 5 years horizon in terms of applications if we have this moment of GPT-3 for robot foundation models? I think the following application areas I'm most excited about. The first is programmable factories. I think factories and industrial use cases are probably the first to be tackled because they're more regular and also more structured and less demanding on safety. You can you don't need humans to be around robots inside a factory, right? Like you can have the factory basically walled off, and then the robots operate themselves. So it doesn't need very strict safety criterion, and also like the manufacturing process is quite well understood with very good specifications. So it doesn't need too much generalization. It does need some generalization, but not too much. And if we have a GPT-3 or GPT-4 level robot foundation model, then we can quickly reprogram a set of intelligent robots so they can manufacture a new product almost overnight. And you can basically show the robots, let's say, a few demonstrations, and then you can program them, right? You program by demonstration, by data, instead of programming by hand. And that's why like robots are very difficult to be reprogrammed these days because people do it by hand. And then big factories are really hard to repivot. You need months, if not years, of expertise to reprogram something. But once we have these foundation models, the factories will be a lot more programmable. So I think that's one of the first areas. And the second area I'm excited about, also really regular, very structured, and isn't that demanding on safety, is self-driving wet labs. A lot of scientific experiments, like in chemistry or in drug discovery, are still carried out by humans, right? Even though there are special equipment, right, to do kind of chemical mixing, that people don't do it by hand anymore. But think about those biology experiments, right? Still, there are a lot of humans in the process using those equipments. We can completely replace that with an automated robot pipeline. And it's going to look very similar to a programmable factory, but this time applied to scientific discoveries. So you can collect data and program this whole line by demonstration instead of by like hard coding. And then there is the agentic fleet. So we discuss a lot about single robot, but what about kind of having this like hive mind of a whole fleet of robots all working together? Then we can run these agentic flows, right? These multi-agent flows controlled by a central LLM brain to break down and distribute a task to a whole fleet of robots. So they can better support these factory assembly lines and also multi-stage, right? Like scientific experimentation. And then finally, home use. I think home use is just a lot harder to be fully automated. It's way more unstructured, right? Every house is messy in a different way. And then you for sure have a lot of safety concerns, right? There are kids, elderly people, and these robots, right? Like they weigh a lot, and it's not fun having any of those robots fall down, and fall on a person, right? So I think home use, and then there's also like privacy and all of those concerns. I would say home use is still a bit out there, but I really wish that we can see that in 5 years. If not 5 years, definitely by 2040.
Very inspiring examples and application areas. Thank you, Jim.